Okay, so if we want to establish a good or an optimal na model such that the model can generalize well on unseen data, so in other words, we achieve optimal na performance both on the training and the test na set, then we must establish a good bias-variance trade-off. So we can see here in the plot the training and the testing error as the complexity of the model increases. Okay, so the red line represents the test na error, while the blue line represents the train na error. So we can see in the plot that as the model's complexity increases, or from a simple to a more complex na model, or in some textbooks, more flexible na models, the training error is decreasing. And the testing error, on the other hand, is increasing. Okay, so at the beginning of the training, we can see that both the training and the testing error is low. Okay, or we have high prediction errors. And as we train it longer, then we can see that initially both the training and testing error are decreasing. But as it gets longer, or as the model becomes more complex, then the testing error begins to increase, while the training error monotonically decreases. Okay, so what we want to have is to find a good fit or a good model such that we achieve a low bias and a low variance. So in other words, we want that the model can be able to capture the real shape of the data set, okay, so that we can minimize the errors. And we want that the errors are not spread out or are as close to each other. Okay, so we can see in the plot that as the model becomes more complex, the tendency is the model could overfit. Okay, overfitting means that the model learns including the randomness in the data, like the noise, and we don't want that, because if the model is overfitted, then it cannot generalize well on new and seen data. And we can see in the plot that indeed the testing error is increasing, and therefore the performance of the model deteriorates. So it is characterized by having a high variance and a low bias, and we don't want that. And we also don't want that the model is too simple or undertrained. Okay, and for example, we have the shape of the data set, and we assume that it is linear. And even if we can see that the shape of the data is curved, but we assume a simple estimate such as a linear method, and it cannot capture the real shape of the data. And so the performance of the model will also deteriorate. And this causes both the training and the testing error to be poor. And having this, or having such assumptions on the shape of the data, will cause us a high bias, but low variance, because even if the estimate is not that sensitive to the data set, so even if we introduce new data set, and it will just introduce a new nudge to the estimate. Okay, so we don't want that as well. We want to have a good fit that have a low bias and a low variance. Okay, and these are the other metrics that we could make use of. We have the mean absolute error, the RMSE, the R squared, okay, etc.